who is the most competent person to introduce our speaker, Fernando Pereira.
It's of course a pleasure to introduce Fernando. Fernando did his PhD at Edinburgh on rule-based natural language processing.
Oh my goodness.
Along the way produced the first publicly available Prolog interpreter, which was used for many years as the only publicly available Prolog interpreter. He then moved, if I remember correctly, to SRI, and from there to AT&T under various names, and briefly went to Whiz-Bang before moving to his present place, the University of Pennsylvania, where he's the chair. And his title is Undirected Graphical Models for Sequence Analysis.
Nice, thank you. So I know that Andrew McCallum was one of my co-conspirators in this work, was here last week or so. So some of what I have to say may have been already said by him. So if you're going to slowly tell me, move on, we've heard that before. On the other hand, if this might be an opportunity to hear some of the things he had to say again, so that might, and go into more detail. So the main ideas I'm going to talk about with joint work with Andrew and with John Lafferty, and then I've been working with a student at Penn, Fei Shah, on some of the most recent experimental results. So what is the sort of the motivation for this work? I mean, the original motivation that Andrew and I had when we started working along in this area was information extraction. And many of you, I'm sure, have heard about the sort of basic idea of information extraction. You have some text, you're interested in finding entities and relationships expressing that text. So this is some standard example. You're looking for persons, you're looking for organizations, you might be looking for some relations between them. And one approach to information extraction that has been very popular is to think of the problem as a sort of a finite state problem where, although of course there's a serious oversimplification, where you're trying to construct some finite state pattern matches that identify things like, oh, here's something that looks like a person name, followed by who. Something looks like a name because capitalized and is followed by who. So, oh, maybe that's a person name, and so on and so forth. So now people have built those things by hand as a rule-based system for information extraction. That have been fairly successful, but probably the most successful finite state based information extraction systems have been done with hidden Markov models, on which more later. And in one way to think about what we're trying to do here, and which is going to be useful in understanding the rest of the talk, is think about information extraction as labeling. I'm going down this sequence and I'm going to label the tokens with certain labels or states that represent what my intended interpretation of that token. So this is, maybe I label this as a person label, I label this as other, and then here descriptor or whatever it might be, all these tokens throughout there, and then I say, oh, here it's an organization token, and so on and so forth. So in general, it's going to be useful to think about pairs of a sequence of input tokens of some kind and of a sequence of labels. And so that's the problem that we're going to be talking about for discussing the rest of the talk. Now, as I have been talking, I've been talking just about the problem of identifying these entities. But it's also important to identify some relations. And various ways you can think about in doing that. One might be, for instance, you produce one first level of labeling, and then on top of that run another label that maybe uses the original words plus those labels as input, and produces some additional labels that tell you how these things are related. I won't be talking about that. Or you might use certain structural labels, where the label doesn't say just it's a person, but it's a person that is related to something else. But as I say, I won't be talking about those details. I'm just focusing on this problem of sequence labeling. So additional motivation for thinking about this, things like part-of-speech tagging, various kinds of shallow parsing, which I'll talk about later, And recently I've been starting to work on some problems in biological sequence analysis. And which is kind of interesting because it's in some ways it's related, in some similar, but some ways very different from the linguistic case. There are certain local statistics that are very informative about, say, whether I'm in a gene or not in a DNA sequence, but they are insufficient to get the boundaries very accurately. And then there's all these other bits of information, what people in the jargon of that trade call signaling, that tells you, oh, there's this place where the gene starts being translated. Here's a splice site. I won't tell you what these things are. Basically, we have to think about the genetic sequences being decoded by a machine, a biological machine, and that machine needs to notice certain signals that tells you to switch on, start copying, and then switch off, and so on. So trying to guess what those signals are, which they tend to be quite ambiguous, is a very important task in genomics. And in sort of finding ways of combining these two types of information is sort of an activity that a lot of people have been investing a lot of effort. So there are two ways you can think about doing these labeling tasks. One is sort of what I'll call here global labeling, and the other one is going to be called local labeling in a moment. So is to think of the problem abstractly. I'll just try to say, as somehow I have some training set ranging over I here, and they have pairs of an input sequence and a label, and the label sequence, depend on some parameters. And I just realized, which I should have fixed this slide here is a little bit, the notation changes. I use here some lowercase theta, but in the rest of the talk or some of the slides need to be a lambda, capital lambda. So some parameter vector anyway. So you have some model based on some parameter vector, which will be real numbers, and I'm going to have, given that model, I'm going to, with the current settings, I can compute a loss, some loss function. I'll tell you later which loss functions I'm going to be working with. For a particular training instance, saying how basically what is this, which is an objective function that you want to, when you try to find the correct the labeling for a new sequence, you're going to try to minimize that loss or maximize some converse of objective function. I'll get the switching between loss and which you might think, for instance, as might be a minus log probability in the cases we talk about, or might talk about the probability later on, although not all the models I'll talk about are probabilistic. So basically, at training time, we're going to try to find a parameter vector that minimizes the loss of the training data, where the training data pairs of an input sequences X and the label sequences Y. Now, so there are two things here to note, is that when you look at the problem this way, first of all, you need to know how, these objects here are sequences, and these objects here are sequences. Typically, when you're doing a sequence problem, you're going to be looking locally at parts of the sequence, and they are going to have a loss of judgments that you have to combine. So you need to have some common currency, some common scoring mechanism to combine the judgments about the different parts of the sequence into a judgment for the whole sequence, for the labeling of the whole sequence. So you need this common currency. The other thing you need is some efficient algorithm to combine the decisions, some way of combining the individual decisions associated to different parts of the sequence into an entire set of decisions that represents the whole labeling they're going to construct. And so you will see that, of course, and for the people who are familiar with HMMs, that HMMs fall into this story, and so probabilistic methods are a natural way of thinking about these types of labeling decisions. But there's an alternative that's quite widely used, in fact, and until recently had the best results for some of the tasks I'll talk about, which is instead of training to minimize the overall loss, to think of the problem as a succession of classification problems. So at each input position in the sequence, I look at the window of the input, of some kind of window, maybe at the whole input, and I go, on the basis of that, I decide what label do I put here. I might also, so I think, and I use for that some classifier, that technique, site support vector machines, to do that classification. And now, typically I don't want just the class, the label I put at one position to depend only on the input, but also on the labels in the surrounding positions. But now that brings me in the chicken and egg situation. How do I know the labels for the surrounding, if the labels of the surrounding positions depend on each other, how do I kind of get a coherent interpretation? And there are a bunch of different ways that people have tried. I've done that. So the obvious way is you make the label for the current position only depend on the previous labels, the history so far. And so what you then do is, so when you're applying a model like this, so for training, you're just taking each decision as being independent, because you have the context, you have all the labels for training. So you say, okay, I want to create a classifier that gives that will be the most accurate possible for the training data on all the individual labels. And then at sort of a decoding time, I take those classifiers and I run them sequentially, and if I just depend on the previous labels, say, I know already what the previous labels are. Or if these loss measures are commensurable from decision to decision, I can do something like Viterbi decoding. I can accumulate the loss, and I can try all possible labeling so far, organizing the dynamic programming table, and then try the next one. But notice that this is quite different from the previous story. The previous story, I'm optimizing globally the labeling. Here, I'm optimizing each individual decision. And there's no guarantee that optimizing each individual decision is the best thing to do. So now, again, I don't know, I assume I have a pretty broad spread here of people, so some of you are going to be bored. So there's a little bit of tutorial material and a little bit more technical material. So one approach that people have taken to this, which is maybe the most popular to these kinds of sequence problems, is through the use of generative models, where essentially what you model is a stochastic process that generates input sequence labeling pairs. And an example of that is a hidden Markov model. And for reasons that convenient later, I'm going to write down the hidden Markov model in a way that it's not so common in the speech community, but that's the way that in the sort of the graphical models community you like to write a graphical model. You just unfold the hidden Markov model and just think about the sequence of decisions or states at each position. So this is a label or state at position 0, position 1, position 2, etc. And the corresponding observations. So these are my, so here would be some kind of a class, say person or company or whatever it may be for the information extraction case, and here is the word that you observe at the token you observe at that position. And so you unfold that. It is kind of, this notation is convenient later on. So this is the standard picture that you have for when you're wearing your graphical models hat. For a hidden Markov model, and we know how to work with these. Now, let me skip that and I'll get back to it. So, Andrew McCallum in particular did some interesting work on doing information extraction with hidden Markov models. And as I explained the idea before, the states correspond to same, so this was for papers, titles, and authors, and things like that. Each state represents some particular type of information that I'm getting. So the observations would be words, and the states would be the fields to extract. So this is an actual the topology of particular HMM. I'm now seeing not as a state machine rather than that unfolded form. for doing extraction for Quora, which is this thing that looks at papers and gets the titles and the authors and the affiliations. So this has been a very popular way of doing things. However, there's some problems. So the main problem is that there are lots of overlapping features of the input that you'd like to deal with in your model. But the hidden Markov model really doesn't help you there, because the hidden Markov model is saying, okay, I'm at this state, what's the probability of observing that word at this state? It doesn't say, well, what's the probability of observing a word that's capitalized and ends in ing? So often, particularly for unknown words, this is a very useful thing to do. Also for, essentially, even for dealing with sparse data problems, it's a good thing to do, even if the words are known. For doing other information extraction tasks, you might want a lot of other things. You might want to know, what font is the word type printed in, what the color of the surrounding the background might be, and so on and so forth. Or you might be looking not just at single tokens, but whole lines, for instance, or layout in various ways. And so generative models, not only HMS, but any kind of generative model, doesn't really handle these very well. And so we're going to talk about some alternative ways. So the generative model, you have you think of the problem as in terms of stochastic process that generates pairs of a sequence of its labeling. Here we're going to think instead, for the rest of the talk, in conditional models, where you're thinking is the probability of a labeling or a state sequence given an observation sequence. But just to reinforce that point, one thing you might want to do, and I'll talk about some results of it later, is the following. Well, you have all these features of the input that you're talking about, ends in ing, is capitalized. So I could think about treating these features as independent features given the class. So like essentially thinking of a naive Bayes model at each position in the input. So, that's not an unreasonable thing. We know that naive Bayes performs pretty well for document classification. Why not for this task? Of course, you're making this bad assumption that these features are conditionally independent given the state. But, that was a bad assumption for document classification too, and still it performed reasonably well. The other thing you could imagine in doing is, well, you might use general graphical models techniques and say, well, maybe there's some arrow from here to there. And I would just add a few more arrows here and then train that way. Now, the problem with that, as many of you know, is that trees are good for these types of problems. It allows you to do essentially linear time inference and decoding, but trees require conditional independence given the label. And that's unrealistic, but if you go away from trees, the problems become computationally intractable. So there was some anxiety about this, and we had that couldn't we do better? And so we started looking at alternatives. So the first alternative we thought about was this notion of thinking about a local conditional model, rather than we weren't really thinking about in this perspective I gave, where you have a whole input sequence and whole label sequence or state sequence. I was thinking, well, let's look at the individual classification at each point. Can we treat that in a different way? Then, say, in an HMM, the individual information of each point, probability information at each point is a probability of a state given the previous state and the probability of an observation given the state. So what we considered doing is, what about thinking about the problem of, instead of a generative process, a process that, given an observation in the previous state, tells us the next state. So notice that it's like a classifier, right? For each previous state, I have a classifier that looks at the observation and gives me a probability distribution of the next state. So in fact, we're going to use this notation P sub to emphasize that we have all these functions, probability density functions corresponding to the classifiers for each of the origin, the source states. So you one way depicting that is you have, for each state, I have a black box that tells me, looks at the observation and gives me the distribution over states. So now, how do we model this? Well, we're going to essentially use an exponential model in sort of a max sense style. So we're going to consider a set of features of the observation, say what the word might be at that position, whether it's capitalized, what its context might be, and we're going to consider a set of predicates, and then we're going to consider a set of features which are one of these observation predicates, something that just looks at the input, and a choice of a destination state. So the features are going to be essentially pairs of a predicate and a destination state. And then we're just going to use a per state conditional model. So it's going to be the probability of, so for the source state, we have the probability of a destination state given the observation is going to be in the standard form for a maxent model.
Is the lambda a function of S prime also?
Lambda f is ranging over features. So remember the.
So the S prime only is in the denominator of it? The outgoing the state from which you go out, which is the S prime.
It's S prime.
And is that the only place? I mean, the lambdas are independent of S prime.
Remember the features depend. F is an index. This is an index here. F is an index that range. That's it's 1 to n, but a feature pertains only to one destination. Oh, I see what you mean. There's maybe a type of. The answer is the features depend. Where I'm going back, right? The features here depend on. I see what you mean. Yes, there's a little notation inconsistency here. The features depend on the source and the destination state. Sorry, which is what I use later. I noticed that you are right. I mean, the previous slide is a little clear on that. So these you can think these Fs as sort of as a group index that essentially each F is a source state, a destination state, and a predicate. So these are little triples underneath. But I want to simplify the notation without having to index over all those things. Sorry, now, each of these models can be trained separately because essentially it's a classification. I'm just going to look at each position in the input, where I go into, what the observation features are. And with a model like that, I can decode by Viterbi. And also there's a generalization to partially labeled data. That is, in general, I could imagine that what I have, my label, so here's the standard situation. I have a label that says person. But in fact, there are multiple states that my model might want to have for person. Now, first name, middle name, last name. Now, in my labeling for training, I don't know which one is it. It is. So there are multiple states that produce the same label, person. And to do that, it's a partially labeled case. Now you can extend, there's also a straightforward extension of Baum-Welch to this case, where you basically try, which I won't go into here. So this is sort of a nice idea. This is sort of in fact, a sort of a summary of what's underneath, for instance, the maxent tagger of Advait Ratnaparkis, among other things. So the application we started with was this separating questions and answers in internet facts, which is a simple problem, doesn't have a lot of data, so it's one that you can experiment with different possibilities. And in the case where layout is very important. It's not just the words, but in which context. There's blank space, there's a little thing like that says, oh, this looks like a label of a question, and so on. So there's a lot of contextual information that's useful. So you have some experimental data labeled in the appropriate way. And what the results I'm going to describe is for each fact we have a bunch of 38 files, train on one file and test on the other as an average. And we use a bunch of features that seem appropriate. Things like the line begins with a number, and so on, so it contains a question mark. It's all in terms of lines. The features are all in terms of lines because lines seem to be the right unit for the internet facts. And we tested 4 models here. One is a maximum entropy classifier for each line independently. So we basically train think of the problem as a document classification problem where the documents are lines. The second one is just an HMM that emits the observed words, and so the obvious HMM. The third one is that picture I gave you before. Remember the naive Bayes at each position? So it's called feature HMM. So basically, at each state, I generate all the features independently. And finally, is this thing that I've been describing, which we call the maximum entropy Markov model. And I wouldn't be telling you this if the table didn't look like, the results didn't look like this. So you see that basically so segmentation precision and recall are the obvious things with respect to the segments that you are producing here, question answer. One thing to note is we lose substantially by looking at, so these two this is the cases where you're using the same featural representation. But the naive Bayes technique versus the Maxent technique really performs much worse. This is not always the case, for instance, for document classification. Naive Bayes in some cases performs. It is the case where if you have little data that, although some theoretical arguments would say that with small amounts of data, these should be performing better than that. In fact, we see that with that in this, at least in this case, this approach performs much better than that, and all the other ones sort of are much worse. Clearly, state structure matters, or for this, or because these are the same classifier, except that this one is independent where you are. This one it's dependent. You have information of where you came from. Now, this is all very well and nice, but it has a problem. Now, this problem we call the label bias problem. I don't know whether Andrew talked about this a little bit, and this is sort of a source of confusion often. So I'm going to talk about it again, and maybe when you say it twice, it will make it. So there are different ways of thinking about this problem. Now, one thing is, the first person who pointed this out to me, by the way, is Michael Collins, and with the following anecdote. When I was describing to him the previous results, he said, "Oh, but there's a problem with this," and he tried to explain what it was, and it was kind of, we struggled. I didn't understand what he was saying, and it just took a while. And then he said, that's one of the reasons why the people at BBN who are doing information extraction still use HMMs rather than Maxent. And I said, well, those guys know what they're doing. So if they are doing that, there's really a problem here. And there's another anecdote which is interesting, is that if you look at carefully at that Waite's work on tagging and parsing, he does beam search because the full Viterbi decoding, say even the tagging would not be practical because there are too many states. And he uses a very narrow beam. And the question is why? If you had a very narrow beam, wouldn't you lose the correct labeling very often? And it turns out he doesn't. He actually did some experiments, if you increase the beam, and things don't get any better. So that's a puzzle, because if you are doing Viterbi decoding, you have the hope that the future is going to influence how you decide about the present. And yet, it seemed to be that actually didn't really need to know that much about the future to perform there. Well, it turns out that these things all are symptoms of one and the same problem. And this is the problem that later on, we found out that Leon Botu, who used to be at AT&T, found in trying to use discriminative training for HMMs back in his thesis in '91. And here's my sort of simplest representation of this idea. Suppose I have a model like this, where there's an ambiguity here. So what the story here is, there are some states, and here, if you think about the situation, what we were describing before, given a state, a source state and an observation, I go to a distribution of this destination states. So I'm going to do harden that and say, well, given an observation and a source state and an observation, I go to a destination state, certainly, or almost certainly. I am actually, in the reality, assume that the probability of going, if I'm in state 0, if I see R, I might say the probability of going to 1 is going to be 51%, the probability of going to 4 is 49%. Now, once I am in 1, if I see I, the probability of going to 2 is 99%, and maybe the probability of going to 5 is 1%. Now, notice the following. If I'm in I in 1, and in CI, I say, oh, the probability of going to there is 99%. What about if I see O? Well, there's roughly one only place I'm allowing myself to go. So I'm saying I'm really stuck to this branch. Given that, if I see anything, the probability of going there is going to be, I'm going to be certain to go there. Whatever I see, that is, I'm ignoring the input. Now, so the general point is that states which have very few outcomes, and you can generalize this argument to, instead of saying certainty, they're saying what the entropy of the output distribution, the next state distribution is. Basically, if you have a very low entropy of the next state distribution, you're going to be forced to go that way, even though, you go that way, even though the observation is one you've never seen for this transition. Now, if you are thinking HMMs, you say, well, but then you should take a huge penalty because the probability of observing that in this transition is very low. You're not modeling that probability. You're just modeling the conditional probability. So you're not, the fact that you've never seen that observation in this transition is completely irrelevant, and if it's not going to penalize you at all. In fact, if you think log probes for a moment, it says, well, what's the penalty of going from here to there? If I have a no, that that penalty is 0, or just about 0 if there's some little leakage between these things. Whereas on an HMM, I say, what's the probability of observing an O given that I'm in state 1? It's going to be minus infinity. That path is going to be blocked if I have a no, but not with a conditional model. A per state conditional model. Now, the reason I go over this is because there's actually something else that is important, which is, remember when I said early on, there's these types of local models, these ones that do a per state classification. Not necessarily probabilistic models, might be support vector machines. They all suffer from this problem. Every single local model that people have been using for labeling or for parsing suffer from this problem. And it might not be obvious and not be obviously to be, but there's something interesting. For instance, if you now think about the parsing problem rather than the labeling problem, why is it that all successful statistical parsers are based on generative models? Is this an accident? I suspect that it isn't. It is actually the fact that as people thought about the problem, this type of difficulty kind of in one way or another percolated. And in fact, if you look at if you look carefully at Adwaite's parser, this is the same, this problem was there already. He did not need to do any beam search. Of course not, because, any wide search. Because it didn't matter, because the model wasn't able to penalize the decision now. But so a sort of so-so decision now cannot be penalized in the future. Here, what you want is, well, here you don't know what you're going to do, so you should be agnostic until you get further down. But with the model we're using, the further down never informs you of anything. So so basically the only reason for not doing a deterministic parser for add weight is that there's some purely local uncertainty. But if you don't have any kind of propagation from the far future. With the generative parser, with the generative so a stochastic context-free grammar using the usual way, you do have that capability of blocking out parsers from information widely spread in different places in the input. This may be obvious to you, but certainly wasn't obvious to me when I was thinking about these things originally. So, I mean, now that example is a toy example, and you could say, oh, well, what you really want is to merge these two states. And then, yes?
It follows from your assumption that the individual classifiers look only over a local region, right?
They could, on the input side, they could look at, okay, clearly a classifier just from practicality cannot look indefinitely into the future because you don't know what indefinite is. The classifier has to convert. If you're using any classification technique known to mankind, it's going to be over a vector. This vector is going to have a length, right? So I could look 10 words into the future, maybe, but that would still not be the whole future. And you're right that one of the reasons was something like I think one of the reasons why Hadwick's parser works so well as it does is because he's looking several tokens into the future on the classification side. He's not just looking at the current word, but also the next two words in the future. But he's still myopic. So what? So anyway, so that you could try to do various things which might help. But what I'm going to talk about is this kind of undirected graphical models, which you call conditional random fields, which you've heard about before, and you're going to hear about more now. So the main point is the following. Let's go back to this global model that I started talking about. I'm going to look at probability of a whole label sequence or output sequence given an observation sequence. Now, I'm going to allow arbitrary dependencies on the observations. But I'm going to constrain the dependencies within the labels so that the inference and decoding are tractable. Now, one thing that is sort of not obvious the first time you see this, but I think it's quite important, is that if you are using HMS, you have one of the or any and the same. By the way, the same argument flies for stochastic for probabilistic grammars. So for the context-free case rather than the finite state case, use the states or the known terminals to encode not only your decision but also some memory of the history, because you need that to condition your future decisions. Now, in this scheme, you don't, because you put or at least for bounded memory, you can just let that come out of the dependencies on the input without having to encode it into the state. So you can actually do the same job that you would do with an HMM with lots of states, with a model with far fewer, this kind that I'm going to discuss, with far fewer states. And this could be kind of interesting thing for parsing, at least, although I haven't explored that yet. So the picture, when I think that Andrew gave you this picture last week, or at least I saw this picture on Sanjeev's board, so which suggests that, but I'm going to repeat it because I think it's bears some thinking about. Is the following: I have my states, labels, whatever I want to call them here. Oh, in fact, I changed notation. That should be an S. Sorry. And I have my observations. I was doing some last minute editing to make notation uniform, and I didn't quite completely succeed. It should be an O, not an X, sorry. And I go, so then in the most general picture, I'm thinking about of a chain of states or labels with dependencies between successive ones. And then these depend on and these dependencies are conditioned on the whole sequence. Now, in general, of course, you don't condition, in practice, you don't really condition on the whole sequence. You condition on some features of the sequence. So this is going to be Markov on, sorry, my change in notation didn't quite completely succeed here. This is Markov on this, on the state sequence, conditional dependencies on the input. And the model is going to be an exponential model, which is global for the whole sequence problem. So there's going to be a normalization on the observations, and the probability of some state sequence given observation sequence is going to be a product over positions. I is a position going over the sequence of the terms of this form, where this is a lambda f is some feature. Now features here are some class of functions that I've given to us. And these functions depend on four things: the previous state, the current state, the whole observation sequence, and where I am in the sequence. Now, of course, the real features are going to say, well, the word at position I is the, or the word before was a noun, or the word the next word ends in ing, or but it could be also things like the average number of nouns in the sentence is less than 0.5, say. And so the features are going to represent interactions between states. Also could be, if you imagine you have some features that ignore one of these, could also be just features that talk about the distribution of individual states. So here's kind of a dense slide, but actually it's a useful slide to think about. Think of an HMM originally. The probability of a state sequence given an observation sequence is proportional to a product of terms, some which involve just states, and some that involve observation in a state. In the model we talked about before, maximated Markov models, there's also a dependency of, so there's some normalization, it's a product, there's some normalization terms, one at each position, and then there's you can take an encode, sort of the counterpart of that HMM is going to be an MEMM where there are two, in the exponent there are sum of two pieces, one corresponding to interactions between successive states, and the other one interactions between observations and states. In the conditional random field, the picture is the same, exactly, except that the normalization moves out of the product. That's all the difference there is. Instead of having a normalization per decision, you have a global normalization. It's very small change.
Actually, when you do pull that normalization outside of the product, you've changed your model back to be a Markov equivalent to the HMM.
No, it is not.
No, it is, because the conditional you're representing the conditional distribution of S given O for the CRF. But if you did the same thing, you could still have a conditional criterion for an HMM where you're representing probability of S given O. And it's the underlying statistical model represents the same set of independence statements.
Not on the observations.
Yeah, well, we can talk
Not on observations, no, because in fact, notice that this model has a per state normalization or per observation normalization, which this one does not. So in fact, you can have the following thing you cannot have in an HMM. You can have, let's say, the scale of these things here is such that you could favor, and there is no guarantee that the being in a particular state, since this model has no distribution over states, over observations, it doesn't model the distribution of the observations. It need not be consistent with the distribution of observation sequences. I mean, this is sort of a simple way to say that I don't think you're right. I mean, you just cannot. There could be a model. There is no
We're not talking about what you're actually representing in terms of quantities, like data structures. I'm talking more about the markup equivalence of the statistical model that underlies what you're actually doing. Because the CRF is an exponential model.
Mm-hmm.
And basically it's just a bunch of functions, potential functions, with some normalization going. And you're representing the conditional distribution of that. So you're normalizing it so you get P of S given out.
Mm-hmm.
But the underlying model, the statistical dependencies that's being represented, which is different than the data structures that you're using, are the same as the HMM.
I think we'll have to talk about it later because I didn't understand what you said.
The HMM is a special case of that, right?
The HMM is a special case in the sense, the HMM, right? I can take the HMM and represent it in that form.
But you could write that there.
But the point is, I could move some terms under the product, which I cannot do here.
But the thing is, you're not representing any longer the P of S given S minus 1 and O's in the CRFs. That's no longer there because of the global normalization.
The P of S given?
Like that you got in the MEMM. You've got the
Oh,
P of S
I know.
No, so it's not really, it's not a discriminative model. It's sort of a generative model, and the criterion function that you're optimizing is a discriminative criterion.
No, it's not a generative model. It doesn't give a distribution of the observations.
May I
Yeah.
suggest something? I mean, the fact is that Jeff is right if this is a correct formula. Now, you may have found out something in that formula.
Why?
Well, because the exponent with the lambda f st minus 1 is like the pst given
I know.
st minus 1, and the other thing is like the other thing, and consequently,
But-
formally, this formula looks
No.
precisely like the other one.
Looks, but it isn't because the normalization is outside here.
I think everybody agrees that an HMM is a special case of a CRF.
Oh
And
yeah,
a CRF and an MEMM are not special cases of each other.
that's right.
Okay. Is there another point being made?
Wait. If that's the point that was being made, no, that I agree. But the converse doesn't go. That is, this is not the same as this. The question of there's a way. Let me just say one thing. There's a way of thinking of an HMM, of discriminatively training an HMM, which is this story. Now, if that's what you're trying to say,
I'm just saying it's
Yeah.
the difference between the CRF is an undirected graph, and the HMM you can represent it as either a directed or an undirected graph, but they actually correspond to the same underlying model.
If you express it as a graphical model, the dependencies between the HMM and CRF are the same.
the cliques are the same.
In the MEMF, it's different because you've got a three-way dependency.
Okay.
I think that's the only point.
Let us move on. We get it better.
So one thing that's worth doing is noticing is the following. When you doing decoding with a model like this, you get, it's trivial algebra to show that what you're doing is computing the argmax of a linear function, which is the inner product of your parameter vector and a feature vector, which is where the feature vector is simply the coordinate of the feature vector for feature f is simply the sum over all positions of that feature function. So, sort of looking at this, you say that from the point of view of decoding, this is very much like a linear classifier. So in fact, one way to think about what we're doing is, well, we're doing linear sequence models. There's this class of linear sequence models which people normally haven't talked about much, of which they all decode in the same way, and the only thing that varies is how you train them. And this is a nice picture because it's very much like in classification, right? In classification, you have linear discriminant functions that you can train in many different ways. You can, whether you use perceptron or naive Bayes, you can think of it as one that you train in a particular way, or support vector machines. All of them are the same type of discriminant trained in different ways. And the point to make is you can think about sequences exactly in the same way. So now, efficient estimation of for these things. So there's a sort of a nice way of thinking of the problem in terms of matrices, where these matrices essentially tells you what is the score, given the observations, what's the score associated going from state S to state S prime, sorry, S prime to state S at position T, and then you can rewrite the conditional probability of S given O in the form that is given there, and the normalization you can also write as a sort of a particular position in the product of these matrices over each position. So now you have a product of matrices, and sort of when you look at the product of matrices like that, you immediately start thinking about forward-backward. So in fact, there's sort of you can sort of take your standard forward-backward story and apply it to this quite directly. Now, if you have any function which is additive along state sequences, which is called what I call here a path function, then the expectation of that function, given according to the model of that function, which is given by this, is the probability. So the expectation for a given particular input, so we're fixing the input O, is going to be the probability of that particular state sequence times the value of the function in that state sequence. Can be rewritten, since the function is additive, in the following way. This should be if the g's are independent of the position, and so in fact where the probability of S and of going from S prime to S at position O is given as given by this, where this is the forward probability. It's not really a probability, it's a forward score of S prime. This is the matrix between S prime and S, and this is the backward score of S. And all of this has to be divided by the normalization. The normalization itself is also computed by forward backwards, because that's a particular case of something of this type. So for training then, if we're going to maximize the log likelihood of some training data, ranging in a way K's ranges over the training instances, the gradient of the log likelihood has this very nice form. It's going to be the sum over all training instances is the count of each feature in each instance, so the sum of the feature over the training instances, minus the expectation of the feature over the training instances. And it turns out that expectations can be computed by forward backward, because that expectation is going to be the rate there's actually two forward backward steps. One has to do with you use the let me stop for a minute. You have to compute the normalization, which is forward backward, and then you have to compute the actual counts, which are also done in the forward backward computation. Now, there's one nice aside here. The partially observable case, which I didn't talk about before, you can simply do is replace this count by an expectation over the paths compatible with your partial observations, which you can again do by forward backward. So you actually have two forward backward steps. One for the computing the pseudo counts compatible with the observations, and the one for computing the expectations over any paths, even compatible not with the observations. So now you have this gradient. Well, how are you going to? So now you can use any gradient method, and we ended up using. After struggling with iterative scaling for a number of months and going nowhere, very, very slowly, we moved into conjugate gradient. And like a couple of things to say. Let me see. Oh, I'll talk about that in a minute. So let me skip this and go to some. Okay, let me talk about party speech tagging. Let's skip the previous thing.
Why did you even consider it?
Sorry?
Why did you even consider iterative scaling?
Why? Because, what, we didn't know any better. What are you going to say? Well, why have so many people consider iterative scaling?
Because for constraint satisfaction, it makes sense, but that's not quite the model you have here.
What? People training these types of models with iterative scaling all over the place. Yes. I mean, no, they didn't listen to you. I mean, I know. But no, there's no, as far as I know, there is no reason. I mean, except that it looks nice on the page. But
exactly, I mean, it's very aesthetically satisfying.
yes, and computationally hopeless.
No, but it's a kind of a nice thing that it works.
Well, I know, I agree. It's nice. It's pretty. It has some information, geometric interpretation, all those good things, and it is maybe there's so John Lafferty claims that some of his students in class have come up with a tighter version of the bound that gives you much better performance. I'm waiting to see.
Well, just to throw out a research topic, it might be possible to do a hybrid. So there is a hybrid between EM and conjugate gradient by Jamshid and Bedrich, which is like a self-scaling version of conjugate gradient. It uses, I believe, an auxiliary function the way EM does, and so you might wonder if you could do something similar with iterative scaling.
So one first thing we did, just kind of get to go to the one thing we did a while ago, this is actually before we were using conjugate gradient, was to just compare like with like. We did a very simple part-of-speech tagging, not competitive part-of-speech tagging in the sense we didn't use all the features we could use, but just try to do the following. Suppose I had just an HMM where the states correspond to part-of-speech tag. So this was kind of the simplest possible HMM model. And you notice, in fact, that HMM and MEMM, which uses where the features are only what is the word. So in fact, that MEMM and that HMM and the CRF also, they all have effectively the same parameterization. So you can think of the CRF as the quantity. This CRF is that HMM trained discriminatively, effectively. Now, the MEMM, so one thing to note is the MEMM performs worse. This is not so surprising because you're not looking, since this model is so simple, you're not looking in the future at all in the MEMM, whereas the HMM can see the future and you get worse performance. So this is sort of evidence that even for part-of-speech tagging, at least with a simple part-of-speach tag, this label bias problem really hurts. The CRF, I mean, these probably are not statistically actually, they are because of this data set, but it's not enormous improvement here. Now, we were using iterative scaling then. I don't know whether if I had been using conjugate gradient, whether I would get better, because iterative scaling was flattening out for numerical reasons. So, this is a question that we didn't explore since then. Now, if I throw in a bunch of features, like spelling features, like ing and so on, of course, both of these models are going to do better than that. But again, the conditional random field does substantially better than MEMM, as you might expect. But it's nice.
The probability of all the vocabulary?
Sorry? This is a very simple model, right?
So what's the probability of an auto vocabulary?
I don't know for one thing. It's somewhere in a paper, I think, but I can't remember now.
So the difference between the plus models is that you had features from the future in the past as well?
Sorry? No. These are just the spelling features. You're just looking at the present token.
Okay, so you didn't try adding them to the HMM?
How could I?
Well, they're observations or they're not observations that you.
They are observations, but they are not in the.
You can have a generative model for observations you haven't seen before, the same as you do in speech.
Well,
I mean, you use a spelling model on the word level.
yeah, sure, I can do that, and I can spend the rest of my life trying to get it right. I mean,
Well, you run this
these are awful hacks, it doesn't make
you do
any
it by
sense.
machine composition. It's easy.
Sorry?
If you do it by machine composition, in principle, it should be easy.
Oh, yeah, I mean, yeah, sure, if you have all the software and so on, yeah, it's easy. I
You
mean,
wrote this up.
I didn't have all the
You
software.
just
No.
didn't take it from AT&T.
Yeah, sorry?
Maybe you weren't allowed to take it from AT&T.
No, I definitely not. And anyway, but this was just trying to identify. Now, this was just trying to identify the particulars that made these things different. Not try to get the best part of speech tagging. Now, recently we've been doing playing with shallow parsing tasks, the NP non-phrase chunking from part-of-speech tag text. So the part-of-speech tags are actually the Brill tags. They are not the correct tags. This is a standard task that people have used for shallow parsing. And so here's some recent results. It's nice to know that. So this is the best, most recent that I know method, which is where essentially they train, it's a local model. They train a bunch of classifiers, which are sport vector machines. They train 8 of them, and 4 look forward and depend on the previous tags, and 4 work backward and depend on the future tags. And then they vote.
Which is the CRF.
This is ours.
So what you now described about looking forward.
This was this.
This is it.
The next, as of the published results, is the best I know. This is using a version of Winnow. It's a local classification method that's the IBM guys. And this is Michael Collins' recent work on the voted perceptron. Now, not all of these use exactly the same features for various reasons. So one thing I want to do actually is to do that and that, exactly the same features, which I should be able to do once my student comes back to vacation, and see whether there's any advantage over training. So remember, as I said, this turns out to be a linear model, right? In fact, I won't have time to go in that. But this is exactly the same decoding, but a different training. So it's an obvious question to ask is, does the difference in training matter? So it will be fairly easy to change our code to do voted perceptron rather than CRF training and see whether there's a major difference or not. We in our training some tricks. First of all, we use to control overfitting. We use Gaussian priors on the weights. A single Gaussian prior for all the weights. Critical things though for training practice. We use preconditioned conjugate gradient, where we with a precondition. For those who know conjugate gradient, there's a preconditioning matrix which in the ideal world would be the Hessian, but the Hessian here is way too expensive to compute. Even the diagonal of the Hessian is way too expensive to compute. So you take a very fast, simple approximation of the diagonal of the Hessian, and you have to make sure that it's is the right thing, that some of the terms are all positive, and if not, you just throw it away, and this makes a huge difference. And there's some various pre-computation and features. And we're using full forward backward. Now you could obviously, in anything that you use forward backward, you can use prune forward backward. Just compute rather than doing this computation over all the paths, you could compute over a subset of the paths. And if we go, for instance, I'm pretty sure if I'm doing part-of-speech tagging with the try tags, I need to do that because there are going to be too many states. Let's skip that. So I told you that sort of an interesting theoretical question is so I told you that this is very similar to linear classification, but there isn't really, the theory of linear classifications has very nice properties, and there's some nice generalization bounds coming out of particularly Vapnik's work. None of that at the moment generalizes to the sequence labeling problems. It would be nice to see how that might work. Michael Collins has some preliminary results in his paper, but they are very weak results in that form. Now, this is straightforwardly conceptually it's straightforward to extend this to parsing. Now, computationally, it is not straightforward. So there's sort of an interesting question of whether, in fact, this is a practical way of doing parsing. I do think it is, but the details remain to be worked out. Now, another interesting thing is, so I was just talking about chain graphs or tree-shaped graphs for the case of parsing. But there's another thing you can say is, oh, forget about these chains. Use loopy belief propagation and work with general graphs. Now, for sequence problems, that might not be a practical thing to do. I don't know. But certainly, there's some really nice results by Ben Tasker and the student Daphne Kohler and Daphne and the other people on doing what they call collective classification. And those of you who were at ACL last couple of weeks ago heard Daphne's talk on that. That's a really, really nice idea. It's basically where I take the graph, the dependencies between the labels, and I'm thinking now, for instance, the labels might be the labels on web pages, and the graph, the links in the graph, there's the graph may correspond to, for instance, links between pages. So I really like that, and I think it's the question is for language problems whether you can find an implementation in a type of a loopy belief propagation that works well in sort of the sequential case that boils down to the algorithms we talked about, and yet works also. It's manageable practically manageable for things which are not for dependencies that are not tree-shaped. Loopy belief propagation is a sort of black magic. It may oscillate, and there's all sorts of bizarre things about it. So I'll stop there. Sorry, it took too long.
Question?
You said that your method tests the same as the Michael Collins. I'm a little confused because if I remember correctly, his method is rescoring and best lists.
No. This is the paper is the EMNLP paper. It's sort of I don't have the title of the paper here. Actually, I have the. It's this. It's you have to look at the EMNLP paper. The paper's there. I'm just looking at it. I mean, I can tell you. I mean, actually, I have a slide. I mean, for those of you who didn't go to his EMNLP talk, this is so cool that it deserves looking at. I just have to show this because it's a really nice idea. So basically, it's a linear classifier or linear labeler. It scores a sequence labeling pair. And what I'm going to tell you, this is the algorithm. And in this algorithm it's nice because there's no complications of conjugate rating and anything like that. A is a vector of weights. Initially is a zero vector. And then they have a number of iterations called epochs in the jargon of perceptron algorithm. And they have n training examples. So you start with A equals 0 and you compute the argmax of AI times the feature vector over so this is so this is, for instance, training instance J. I'm going to compute the best labeling according to the current model. Notice that initially this is 0, so you have to have a tiebreaker of some kind because all of the labelings have the same score. So there's a subtlety about tiebreaking. But now if the labeling you get there is not the labeling the correct labeling according to your training set, you adjust what you're going to do is take that weight vector A and update it by computing the following way. This is the difference between the feature score values So phi, remember, is the feature vector for an instance. So this is the difference between the feature values for the correct labeling versus the feature values for the labeling you just got, which is incorrect. So notice what that does is as features that were stronger in this example, were stronger in the correct thing than the incorrect one, get their weight goes up. For the features that were contrary to the decision, their weight goes down. Otherwise, you keep this weight vector. So now you store all these weight vectors, these AIs, and at the end you average them. That's why it's the voted perceptron. If you're doing perceptron, that would be that A vector would be your final weight vector. But this is actually not quite voted perceptron according to the letter of the law, but it's an approximation of voted perceptron. So this very simple algorithm for training a linear classifier seems to perform very well. Now, there's kind of some question, how fast is it really? There's some theoretical bounds on the number of the so-called mistake bounds that perceptron algorithms have, but the mistake bound for this case is so pessimistic that the number of iterations would be gigantic to get somewhere interesting. But in practice, it seems to converge reasonably well. Now, one interesting point is we were doing forward-backward in the other algorithm. We were considering all the paths. Here we're considering just one path, the best path. Do we lose something? Now, intuitively, it seems that at the beginning, you're losing a lot because there are going to be lots of of paths that have similar scores, and but you're just picking one of them. Whereas with the forward backward, you consider all of the competitors. So my intuition, what that might be completely wrong, is that the algorithm is going to move very slowly at the beginning, and then eventually start moving fairly fast. So this is a practical question to investigate. With the preconditioned conjugate gradient, for tasks of the same kind that he worked on, so the shallow parsing, we're taking like maybe 8 iterations of conjugate gradient which take roughly an hour to perform. So it's a practical question that I don't know the answer to.
1 hour each or 1 hour
Overall.
How does the maximum entropy Markov model differ to around Bucky's Italian model? Because it's not quite the same, is it?
It's the same, really. Yeah. I mean, the crucial thing is you normalize per decision, and that's a bad idea. So it's that is. If you look carefully at this paper and what I say, it just turned out to be very. I was just thinking about the problem. So in that case, in the stacking model, of course, you have a particular notion of what the state is. Anyway, whereas we work in this where you actually impose a particular state topology and so on. But otherwise, it's the same type of model.
When you do the evaluation on sequence labeling, you have 2 things to get right. You have to get the span.
Yeah.
And you have to get the label right. And do you think
these are binary things, right? Because the chunking is an NP non-NP. I'm not doing all the. I mean, we've done all the classes, but for everybody to evaluate on that particular task, that turns that into a set of binary problems. We haven't tried to train it as a single problem with a multi-tag problem. One thing that there's a cost in doing that, which is that the number of the state space gets bigger, and because for that with this quadratic number of states, you may not, training becomes much slower.
I have one more question. Could you actually go back to the CRF equation?
I don't know. Is that one?
Next one.
Yeah, but that's a particular case, notice. That's a particular case where I'm not using a general parameterization of the transitions.
So in that F, you could put a comma O, and it wouldn't change anything in the lowermost. You have lambda F, STM minus 1, comma O.
Oh, I mean, I did that so that it is just looks exactly like the HMM for this particular example.
Yeah, the previous slide.
Yeah, I was using the more general form. Now, the thing to notice is it really depends on what the exact shape of the graphical model you want to implement is. Actually, I don't like to think, on the side, I don't like to thinking of graphical models in terms of edges, in terms of graphs is really a bad idea. I think thinking in terms of hypergraphs is much cleaner. And in that case, what you really think is you have hyperedges that include some part of the observation and a pair of successive states. That's all. Now, they could be, so essentially these terms here would be something that depends on two successive states, some part of that, and they would be different at different positions because, that's a sort of a, so now it could be, so the example I gave you with the very particular case where there are only two kinds of hyper edges, which are like this and like that.
Okay, maybe we should eat lunch.